I have a tendency when I come here to give a new talk every time, and this will be a new talk. I've never given this before, so let's bear with me on this. It even has a new title than what was in the program, but the content will be the same. Same speaker. So I want to start with just a quick rehashing of some of the stuff that Pierre Ledoussal told us yesterday, but this is self-contained. This is, I would call it a physicist's guide to solving or to studying the KPZ equation. Okay, and this will actually serve as my motivation for the developments later in the talk. So the KPZ equation is this object here. It's this model of random interface growth in 1+1 dimension. The first step in this study is to exponentiate it, which is to say just study the stochastic heat equation, this being a perfectly well-posed stochastic PDE. Now, the beauty of studying the stochastic heat equation instead is that if you look at joint moments, so you look at a fixed time t, but different locations x1 through xk, you can show, and this observation goes back to these works from the 80s, that these joint moments, as considered now as a function of t, and then the k locations x1 through xk, actually solve what is called the imaginary time attractive Lieb-Liniger model with delta interaction, or the delta Bose gas, which is here given by this Hamiltonian. If this is unfamiliar to you, just take the case k equals 1. Then it's very easy. When k equals 1, you're just taking the expectation value of both sides. The white noise drops out, and you get that the first moment solves the heat equation. That's quite easy. When you go up to higher k, what happens is that if the x's are near each other, if the x's are far apart from each other, they're seeing independent noise. So it's like each coordinate just evolves according to heat equation. And when they get together, they see this kind of the square of the white noise, which ultimately gives you this delta interaction. Okay? If you really smooth out the noise, you can see this easily as well. Now, once you've identified this, this is what I'll call an integrable autonomous evolution equation, which just says that the moments solve closed equations. Now, you can hope to actually compute what these formulas are, in particular to solve this for particularly nice initial data. The one which will be pervasive throughout the talk is just delta initial data. It's like starting the fundamental solution of the stochastic heat equation. This is sometimes called the narrow wedge solution to KPZ. In any case, the approach which dates back to really the seminal work of Lieb and Liniger in this matter is the spectral approach, the idea of diagonalizing this Hamiltonian, writing down the eigenfunctions, and then trying to just evolve diagonally on those eigenfunctions. Now, the form of the eigenfunctions really, in a sense, go back to this Bethe Ansatz, which is introduced in the context of the XXZ quantum spin chain by Bethe. And this really started the field of quantum integrable systems, really starting in the early 60s. Now, the challenge, of course, is that if you write down eigenfunctions, so the Bethe Ansatz gives you eigenfunctions for this Hamiltonian, there is still a challenge of asking the question of which eigenfunctions participate in a decomposition of initial data. For instance, in a very simple case, if you just have a one-particle system, so now you're looking at the eigenfunctions of the single particle Laplacian. So we know that the eigenfunctions are of the form e to the zx, where z is some complex number. But when you're decomposing L2, you don't do it with respect to all z. You just do z on the imaginary axis. And then when you recompose, this is the Fourier transform, you need to do it with respect to the correct measure, which is just something like 1 over 2 pi. So of course, things will get more complicated. And this goes under the realm of what's called Plancherel theory, which is basically understanding completeness of the Bethe Ansatz, which eigenfunctions participate, and then how to recompose initial data with respect to projections onto these eigenfunctions. So this was developed by, for instance, Heckman and Optim's work. And you can use this really to compute these moments. Okay? I'll have more to say about this sort of stuff later. Now, the fourth step is the one where things go awry, as far as the mathematicians are concerned. Yep. Yeah. So there's attractive case and attractive. Yeah. Okay. So the fourth step is that let's say that you've somehow computed formulas for these moments. What do you do with them? Well, you would like to recover distributional information about the solution to the heat equation, or the stochastic heat equation. As Pierre pointed out yesterday, if you look at these moments, let's say you take all the x's to be the same, so you're just computing the kth moment. That grows super exponentially with k. It grows like e to the k cubed. So in fact, the moment problem is not well posed. So the moments don't determine the distribution, and there's really no rigorous way of reconstructing distributional information about this equation from that. One can proceed in a very formal, as Pierre was saying, kind of guessing or close your eyes and hope manner, and it works. And within physics, this goes under the term of the replica trick. And they were able to, in fact, recover a solution which had been proved rigorously at about the same time by Guillemire, Jeremy Costel, and myself, and also in work of Sasimoto and Spahn. So as a mathematician, I'm going to ask a very simple question, which is just how should I understand what was done? How should I understand, in particular, this step of why did the moment, why was there some very formal calculation dealing with horribly divergent series, which actually somehow in the end gave a formula that made sense?
So,
yep.
Going back to 3.
Yep.
You solve it with special initial. You said you can solve it. Of course, you have a Bethe Ansatz, but you still have to restrict it to special.
Yeah. So for instance, for really being able to reconstruct the moment, well, once you can of course solve and get formulas for general initial data, but the question of the hardness then becomes how do you use these moment formulas to recover distributional information? And that becomes a real kind of combinatorial or analytic problem. And as I'll say in the next slide, really even at the rigorous level, we've only been able to do this for particularly nice initial data, for instance, step initial data or delta initial data. Okay. So what is a possible mathematician's interpretation of this? And here is the mantra, be wise, discretize. Okay? And of course, we've seen this in many contexts. Maybe also regularize or Q-deform, I don't know. We put in we need to go to some suitably nice discrete system, which you can show under perhaps special scalings should converge to the KPZ equation. Now, what does it mean to have a good discrete system? Well, good should mean that it should preserve the algebraic or the integrability properties which were so beautiful about this stochastic heat equation, this connection to a Bose gas. Well, that comes in the form of step 2 and 3. So what 2 asks is that you find some analog of moments. Perhaps you need to do something like the Kohl-Hopf transform, exponentiating, or something of that form. And you want to show that these moments, or perhaps with some quotation marks, solve integrable autonomous systems of evolution equations. So something analogous to the delta Bose gas. Okay. And then, well, what does it mean to be analogous to the delta Bose gas? What it really means is that it's solvable by a Bethe Ansatz, meaning that you can reduce the question of solving this interactive system into solving a direct sum of non-interacting systems with 2-body boundary conditions. This is, in a sense, what it means to be Bethe Ansatz, solvable, at least in coordinate form. I'll explain this. So I'll give an example. I'll explain how the Bethe Ansatz works. Okay? Right now, I'm just giving an outline. And then once you've done that for your nice discrete system, then you want to be able to use the moment formulas. And if you had a nice enough system, then those moment formulas actually would determine the distribution. As we'll see a few examples of where this works. And now you get distributional formulas deformed at the discrete level. And if the system converges, then distributional formulas also converge. And so you've then recovered the formulas, but in a rigorous manner. So you see actually that what happens is the computations at this replica trick level become shadows of rigorous computations at this higher level. Okay. So as I'll explain in the talk, we can do this steps 1 through 3 for a variety of systems. I'll talk about 3 of them. In particular, this last one, the Q-Hahn TASEP, or as I previously named it, crappy convention of Q-mu-nu TASEP, but I'm going to go with this one. And then we can only really do the step 4, the analytic approach, the recovering of distributional information and asymptotics for very special initial conditions. And I'll only deal with one, which is step. There's an overall message in this talk, though, before I jump into the details, which I want to get across, which is that by going to a suitably high combinatorial or algebraic level with sufficient numbers of parameters, tricky analytic issues are resolved. Magical combinatorial identities are demystified. And seemingly disparate systems, for instance, Q-TASEP and ASEP, which we haven't been able to put together before, get brought under a single umbrella. So this is the point I want to explain. I'm going to do this by really focusing on a few examples and how these steps 2 and 3 work. Okay, I'm not going to focus on any asymptotics, really. Okay, so the first discretization of the KPZ equation that I'm going to discuss, and maybe it won't seem like a discretization, but it is a model called Q-TASEP, which was introduced by Borden and myself in our work on McDonald processes. It's a very simple interacting particle system. You can think of it as a model for movement of cars on a highway, where cars start to slow down as they approach the car in front of them. So each position on Z can be inhabited by one and only one particle. We label these the first particle x1 of t, x2 of t, x3, and we follow their locations. Each particle has a little exponential alarm clock, a random rate, and the rate at which it jumps to the right, and it only jumps by one spot, is given by 1 minus q to the gap. So q is a parameter of the game, and it's a number between 0 and 1. So what does this mean? What it means is that as the gap goes to 0, as you are about to hit the guy in front of you, you slow down. And as the gap grows, the rate approaches 1, meaning you see an open highway and you just go at whatever the speed limit is, or higher. Now, what Q does is it controls the length scale on which you start slowing down. Okay, so as Q, in fact, goes to 0, you recover the model of TASEP, which is a very well-studied model. Now, I'm going to argue, and this is what this theorem will say, is that Q-TASEP could be called a completely integrable probabilistic system in the following sense. I'm only looking for step initial data in this theorem. Step initial data just means I start with an infinite sea of packed particles to the left of the origin and empty to the right. So you'd like to be the first guy because you don't see anyone but open space. Now, so that means xn of times 0 is minus n for all n bigger than or equal to 1. Now, I'm going to, just like for KPZ, I did this Kohl-Hopf transform. I'm going to do an analog, which will be a Q-deformed version of exponentiation. What I do is I look at Q to the kind of KPZ type variable, Q to the location of the nth particle at time t plus n. This is just a little affine shift. Okay, so this is really like exponentiating the KPZ equation. Now, I do that, but just as before I looked at multiple different locations, x1 through xk, now I look at multiple different particle labels, n1 through nk. Okay? So, of course, these n's can be all the same. They can be in any order a priori. This is symmetric. I'm going to assume that the n's take a weakly decreasing order. And the reason is that on the right-hand side, the order will matter. The left-hand side, of course, won't matter at all. Now, so I look at the location of particle n1 at time t plus n1. I raise q to that power, and I do that for n1 through nk. Now I take the expectation. This becomes a function of time and then k parameters, n1 through nk. And my claim is that this is given by a very compact formula, which is here written as a k-fold contour integral with respect to k, what I'll call spectral variables, z1 through zk. And then it has a form which, well, will be familiar throughout the talk, which is it has this van der Waals type term divided by a Q-deformed van der Waals. It has a term which is purely multiplicative, and the only place where t and n comes in. It has this sort of extra 1 over z term, and then the contours have a certain nesting structure to respect the denominator here, having this z minus qz behavior. Okay. The reason why I can call this a completely integrable quantum probabilistic system is that these expectations, these q to the xn of t's plus n, these are always numbers between 0 and 1. So knowing all their joint moments completely characterizes the distribution of the system at time t. So here we have enough formulas to characterize the system. Okay. Of course, you can ask, well, how amenable are these types of things to asymptotics? I'm not going to go into that direction, but I will say that if you take all of the n's to be the same, this gives you a kth moment. You can actually do an analog of computing something like a Laplace transform for the one-point distribution of Q-TASEP. You can really push this through all the way to asymptotics, and you can, for instance, recover the KPZ equation asymptotics, the Tracy-Whittem GUE distributions, and all of the sort of analytic stuff that you want from this. So far, this has only been pushed through for one-point formulas. The other remark I have is that this should be thought of in some sense as being the analog of determinantal structure, but these systems are not determinantal. This is the analog of being able to compute correlation functions for this system. And what we're missing so far is a very robust way of extracting asymptotics out of this sort of structure. Okay, I'm not going to go in that direction, as I said. I want to explain where this type of formula comes from and how to put it into a broader context of coordinate Bethe Ansatz and Plancherel theory. Yep. Well, no, we can write it. Well, we can write formulas of this type for any initial data. I'll come to it. Okay. Yep. No, Jeremy, we can. This term will get replaced, but anyway, we'll come to that. Yep.
Or you can formulate your system in terms of algebraic in terms of variance. And then your initial data is like having ER.
Yeah, I guess.
So the formula you have is similar to that expectation value.
Okay, so we should talk about this more, because I haven't pushed it in the direction of any vertex operators. So this would be an interesting question. Okay, so the original proof that we do have of this formula came through the construction through which this process came, which was through Macdonald processes. And this was built on top of the structure of Macdonald symmetric polynomials, which are not so trivial of objects. So the question is there a simpler way of proving this particular formula for step initial data? And that's what I'm going to explain at the moment, and that will kind of throw me into the rest of the talk. So the for the KPZ, or the stochastic heat equation, the mechanism for computing came through this connection to the delta Bose gas, in some form, this duality to the delta Bose gas. So what is the analog of the delta Bose gas here? So this is a model which is called the Q-Boson process. In fact, the analog of delta Bose gas is itself a stochastic process, or it's the generator of a stochastic process. This is lost when you go to the limit in which you get to the KPZ and stochastic heat equation. This is a model that's studied by Stossman and Wadati. It's in the probability parlance, it would be a totally asymmetric zero range process. What it means is each, you have the integer lattice, and above every side of the lattice, you have an arbitrary non-negative number of particles. And what this system does is, in continuous time, you move one particle, let's say the top particle, to the left. And you do that at a rate given by 1 minus q to the height of the system. And this is the same q that's been throughout, the same q that was here and the same q that was here. Okay? So what you can write the generator, well, a convenient coordinate system for keeping track of this system is either in terms of the site occupancy variables or in terms of sort of their ordered location. So here you had 3 particles at position 2. So you have 2, 2, 2, and then you have 1 particle at 1, so you have 1, and then 3 at 0, 0, 0, 0, and so on. So if you write this generator in terms of these coordinates, what you're really doing is you're summing over clusters, and then in each cluster you can decrease the last coordinate by 1, and you do so at a rate 1 minus q to the c. Okay? So how is this related now to the original system, to Q-TASEP? So the relationship is akin to what we saw for the delta Bose gas, which is that if you now consider the expectation of Q-TASEP, so you're taking k different locations, n1 through nk, you consider this expectation from the last page as this thing as a function of time and then the vector of n1 through nk. What system does that solve? Well, in fact, it solves this closed system where it evolves in time as a function of this Q-Boson Hamiltonian in the n variables. This, in other words, can be considered what's called a duality of Markov processes. The generator of the Q-Boson process acts on this sort of operator in the n variables in the same way that the generator of Q-TASEP acts in the x variables. So the two processes intertwine. Now, what this really means from a practical standpoint is that if I wanted to compute these moments, all I need to do is I need to, well, for the correct initial data, I need to be able to solve this equation. Okay? So how do I solve this equation? Okay? So in a real sense, this Q-Boson system is a discretization of the delta Bose gas. So, so Balint, you had asked what does this what does this boundary condition stuff mean? What is this coordinate beta Ansatz? So here I'll explain how the Q-Boson system is coordinate integrable. And of course, this structure goes through down to the level of the delta Boson gas as well. So how are we going to go about solving this? How do you go about diagonalizing this? How do you go about computing this solution to this equation? Unfortunately, this is an inhomogeneous, non-separable system of equations, so it's not a priori so easy. But it does have a nice sort of property, which is that if you consider this Q-Boson process where all of the particles are kind of spread out, so if all of the n's are different, if there are no clusters of size bigger than 1, then the generator is actually quite simple. It's just 1 minus q, and then you take a discrete derivative in each coordinate. It's just the generator of k different particles jumping around freely. So I'm going to define a free generator, which is just this direct sum of the one particle generators. Okay, these are discrete derivatives acting in the ith coordinate. I'm going to also define something I'll call boundary conditions. And what these mean is that a function u satisfies boundary conditions. So a function u is a function of the n variables. If for every I between 1 and k minus 1, the discrete derivative in the ith coordinate minus q times the discrete derivative in the I plus first coordinate applied to u is 0 when evaluated when ni is equal to ni plus 1. So right near the boundary, when you have clusters, this should be enforced. So the proposition, yep.
You always look at the symmetric subspace here, right?
Yeah, so that's going to come. So the proposition is that if I can find a solution to the free evolution equation, the thing which kind of just involves k non-interacting particles, if I can find that solution on zk, so on a larger space, not on a symmetric subspace, not on an ordered subspace, if I can find that solution such that it also satisfies all of these boundary conditions, then the restriction to the ordered sequence of n1s through nks actually satisfies really the Q-Boson evolution equation, the true evolution equation, but only when restricted to this space. You should think of this as an advanced version of the reflection principle. So what happens is here I'll give you a proof of this. So imagine that you have a cluster of 3 particles, n1 equals n2 equals n3, and they've come together. So of course, this equation is no longer correct, but we have a boundary condition, and the boundary condition tells me that I can express the derivative in the direction 1 in terms of q times the derivative in the direction 2. And in fact, in terms of q squared times the derivative in the direction 3. So I can express the derivative in 1 and the derivative in 2 all in terms of the derivative in direction 3. And I get factors q squared, q, and then 1 if I just look at the third term. Now, what is q squared plus q plus 1 times 1 minus q? It's 1 minus q cubed, which is this number. Okay? So that's a proof. So the nice thing now is that if I need to check, let's say here I have a guess, I need to check whether this equation actually satisfies the Q-Boson evolution equation, then all I need to do is I need to check that it satisfies this equation when considered as a function on zk across time, and I need to check that it satisfies the boundary conditions. And if I can do that, then I know that its restriction to the ordered set of the n's actually solves the Q-Boson evolution equation. Then I need to check the initial data. So the free evolution equation, it's very simple to see that the one particle solution is just given by this term here. And then if you take products of these, Leibniz rule tells you that will solve the kind of k particle direct sum. So this term makes sense. This is the free evolution equation. The boundary condition also just corresponds to this term here. If you apply this operator when 2 of the n's are equal to this equation, n only comes in here, you exactly cancel one term in the denominator. And that allows you to deform your contours together, and it gives you an expression which is integrated over 2 identical contours, but which is antisymmetric in 2 variables, and hence 0. So that's a very simple check. Now, as Jeremy said, initial data is tricky. One needs the right terms to get the right initial data. In the case of step initial data, it's very simple. Step initial data corresponds exactly to this term here. And the way that works is, well, when you have step initial data, it just corresponds to this initial data being identically equal to 1 as long as all the n's are positive and otherwise being 0. That's just because step said that, well, at time 0, the particle xn is at position minus n. So this sums up to 0, and q to the 0 is 1. So you can just do a very simple check from residue calculation. If any of the n's are negative, in particular if nk is negative, then there's no residue at 1. This term, you can just take the integral, you get 0. And otherwise, if all the n's are positive, you just expand through a pole at 0, and you get a contribution which you check is 1. So as Jeremy rightly pointed out, it's a real challenge to understand what you should put here if you want a more general type of initial data. And this will come in the form of the Plancherel theory a little bit later in the talk. Before I go there, I want to give you an analog story, but very briefly, for how things work for ASEP. So asymmetric simple exclusion process is another integrable discrete version of the KPZ equation for which a similar story holds. Okay, and again, I'm only going to talk about step initial data. So this is, well, you can also think of this as a traffic model, but you would hate to be on a highway in which people are following the rules of ASEP, because cars move forward and backwards. You jump to the right at rate q, and you jump to the left at rate p, and you never jump on top of each other. So I guess it wouldn't be that bad. P plus q is equal to 1, and q should be bigger than p, meaning there's a net drift to the right. Now, I'll call tau the ratio of p over q. In fact, tau will play the analog of q from Q-TASEP. It'll play a functional analog throughout. There'll just be one slide about this, though. What I'd like to study is how far this system has progressed. And again, I'm talking about step initial data. So I'm just going to study the number of particles that have made it to the right of position y at time t. So this is just a current of particles. So how many guys have made it past the toll booth? Well, again, it's natural not to look at this, but rather to sort of exponentiate that, and which is to say to look at tau raised to that quantity. In fact, for the formula I'll give you, you take some further sort of discrete derivative in the y variable. And this is what I'll call qy. In fact, this is a function of time as well. So the theorem says that if you start ASEP with step initial data, and now you look at a similar thing, you look at a collection of these observables of ASEP indexed by different locations y, y1 through yk, and time, then this is given by a startlingly similar formula to Q-TASEP. Why? Well, we'll get to that. The formula has the same formula. As I said, tau is replacing q. This is a multiplicative term as before, and this is something that kind of looks like 1 over z. The contours are slightly different. The ordering, the strict ordering, is actually not such a limitation. One can do some further combinatorics and really recover things akin to the, let's say, the kth moment of this observable tau to the ny of t. And the proof of this result, in fact, the one that we gave, goes through, again, a form of duality, a relationship between ASEP and an analog of the delta Bose gas. And what is the analog here? It's nothing but ASEP. So ASEP is self-dual. Okay? And it's also solvable by this sort of coordinate Bethe Ansatz, this sort of separability I explained before. Of course, Tracy and Whittam developed this sort of Bethe Ansatz approach for ASEP, and they studied the transition probabilities and proved various determinant formulas. And this really served as the starting point for my participation in this area as well. OK, but here's a question. There are two formulas, both for step initial data, both for, in fact, deformations of TASEP. They look startlingly similar. Well, what's the relationship? How is ASEP and Q-TASEP related? Well, in order to relate them, I need to lift up a level. I need to go a little bit higher. I need to go to a combinatorial level, a discrete time level, and I need to add some parameters. And then at that point, we'll see them coming together. So I'm going to introduce one new thing. This is halfway through the talk, so it's OK to introduce something new, I think. This is something called the Q-Hahn distribution. And this will be the one new thing I'll introduce. This is called the Q-Hahn distribution due to the relationship to the weight measure for Q-Hahn orthogonal polynomials. It's parameterized by three things, q as before, and then two parameters, nu and mu, nu being less than mu, all being between 0 and 1. It involves what is called Q Plancherel symbols, which is AQN is just 1 minus a times 1 minus qa, all the way up to 1 minus q to the n minus 1a. This is a Q-deformed binomial coefficient, and this is some sort of multiplicative terms. If you're unfamiliar with this, which I don't expect you to be, one thing to just orient yourself is that as q goes to 1, this just becomes the binomial distribution. Okay? This has many nice properties. In particular, actually, generalization was studied by Okunkoff earlier in 1997. Here's how they will come up ultimately in the application. And this is a nice calculation that you can sit down and make and to see why these are important. So imagine that you have an associative algebra generated by A and B. And the relationship that AB is equal to alpha AA plus beta BA plus gamma BB. Okay? Now, I'm going to take these alphas, I'll express them in a parameterization involving q and nu. All that means is that the sum of alpha plus beta plus gamma is 1. So I'll just assume alpha plus beta is gamma is 1. And then p is just some arbitrary parameter expressed in terms of nu and mu. Now, if I take this expression, which looks a lot like the usual binomial expression, except the a's and the b's are non-commutative. They respect this. If I write pa and 1 minus pb, I raise it to the nth power. I get all sorts of terms out of order. Now, I do a normal ordering, so I have the a's before the b's, and I gather the coefficients, and I get exactly this Q-Hahn distribution describing the coefficients of this expansion. Okay? This is how they come up naturally. Okay? And this is what's going to be the important thing. Now, this object is going to be used to define two processes, two discrete time deformations of Q-TASEP and Q-Boson process, as well as and this is what I call the Q-Hahn TASEP and the Q-Hahn boson process. Okay? So what is this? It's actually a very simple process if you just close your eyes and forget what the formula was for this. What it is, so here's Q-TASEP. What it is it's a process in discrete time. Each particle, again, it's an interacting particle system. Each particle chooses a random jump location. So it can jump more than nearest neighbor, and it will jump either, it'll stay in its same spot, or jump 1, 2, 3, anywhere up to the distance to the next particle. And it does so as a function of this distribution. So given that you're choosing numbers between 0 and gap, you choose any number j between 0 and gap. So this distribution is supported on the numbers j in 0 through m. So here in particular, j between 0 and gap. Okay? So each particle does that independently, and then when you clap your hands, they all jump to the next location. Okay? So it's a discrete time version of Q-TASEP. I'll give you how it degenerates to Q-TASEP in just a moment. The other process is in fact, it actually corresponds to the evolution of the gaps of this system. This is the Q-Hahn boson process, and it's a zero-range process, but in discrete time. What happens is you have, again, particles sitting over each location in Z, and you choose out of, if you, let's say, have Y3 particles in position 3, you choose a subset J of them according to this same Q-Hahn distribution, and when you clap your hands, all the particles move to the left that have been designated to move. Okay, so these, I had called these by Q mu nu before because of these parameters. Q-Hahn is a better name. Okay, so what's going to happen is I'm going to show you that, in fact, these two systems are really parallel to the Q-Boson system, or the Q-TASEP and Q-Boson system. They have the same structure, but in fact, in a sense, which I'll make clear later, they also sit above ASEP. Okay, so here, just to put, again, since these are new objects, let me put them in some perspective. Let me describe a few simple degenerations of these processes. If you take the parameter nu equal to 0, this term, both terms simplify, you get a slightly simpler transition probability, which was studied by Borodin and myself, again, in the context of McDonald processes. You can take a limit. You set the parameter nu is 0 and mu is epsilon. You take a limit to continuous time, and you get back Q-TASEP and Q-Boson if you take it for the other one. Here's another nice limit, which is that you take both nu and mu to be very close to Q. That has the effect of kind of this first term tending to be like epsilon. So you, again, need to speed things up. And you get a nice system, which is called a multi-particle hopping asymmetric diffusion process. What happens is it's a continuous time process, and each particle jumps in continuous time according to exponential rates to any location between you and the next particle at a rate given by this q inverse minus 1 over q to the minus j minus 1. If you took the limit of q to 1, you get actually a very simple rate, which is just you jump distance j at rate 1 over j. So you jump distance 7 at rate 1 over 7, anywhere between you and the next guy. If you took the limit q to infinity, you just jump at rate 1 to any location between you and the next guy. So this is one of many degenerations that can be studied of these processes. Okay? And so most of what I'll say can be degenerated to these levels as well. Okay, so the critical relationship which held prior between the TASEP and boson type processes was the duality. It was the fact that moments satisfy closed autonomous evolution equations, and that does persist even once you've deformed up to this q mu nu, or this Q-Hahn level. So if you look again at the same type of observable as before, and you index it as it's a function of time, and then the occupation variables. Here I'm using slightly different coordinates rather than tracking their locations. I'm just tracking the number of particles above site 3. I'll call that y3. And number of particles above site 2 is y2, and so on. So this is the same observable as before. This is a function of time and then these occupation variables. And the theorem is that if I want to know this, then it actually satisfies the closed autonomous evolution equation involving the transition matrix of the Q-Hahn boson process. So this Q-Hahn boson process is an integral discretization of many parameter discretization of Q-TASEP, of the delta Boson gas. I'm going to explain exactly how this is integrable. It really is integrable in the sense of classical Bethe ansatz. But using this and using kind of intuition, I can write down a similar theorem as I did for Q-TASEP and ASEP for step initial data, these moment formulas. And what has really changed is very little. The form of this expression here that involves the n and the t has changed, and that's all. Okay, so now this is a formula which you can start to degenerate in different directions. And you can also write down Fredholm determinant formulas and try to do asymptotics. Okay, so I've explained really step 2 of this program I set out, of B-wise discretize. B-wise discretize, the step 2 said to find systems which have nice integrable evolution equations for these moments. Now I want to describe step 3, which is the spectral theory. It's how to diagonalize these boson-type processes, these integrable equations that you're dual to. So in fact, I have 2 main motivations for this. So one motivation is that somehow all along, maybe it's because the first papers I seriously read were Tracy and Whittam's. I've wanted to understand how ASEP connects to the stuff that I understand perhaps a little bit more algebraically, some things like Q-TASEP. So how are these processes related? And somehow I'd like to develop some umbrella theory relating these processes. In particular, I'd also like to understand what Tracy and Whittam called their magic identities, having to do with certain summation formulas that they discovered. The second motivation is to study general initial data. And as Jeremy pointed out earlier, and as I also point out in my slide, one can, to study general initial data, one can certainly write some formulas down. Asymptotics remains a real challenge as far as general initial data, but I'm only going to go as far as trying to write down formulas for moments. That's the direction I want to push. Okay, so the starting point for what I'll explain was previous work on the Q-Boson spectral theory. This is for this, the continuous time Hamiltonian that we discussed earlier, and this was in a paper that's already come out a year ago, well, maybe 6 months ago, with Borody, Petrov, Sasmoto, and myself, and now we have work which follows up and works at this Q-Hahn level and also includes ASEP. The proofs, however, are quite different, and in fact, by going up a little bit higher, the proofs, in a sense, became a little bit less ad hoc and nicer, in my opinion. So well, if you're interested in what changes between this Q-Boson and the Q-Hahn boson setting, I've written all those terms in magenta, so you'll see that it's not so much. Okay, so from the start, if you remember back to this Q-Hahn boson process, you see that this is not self-adjoint. Particles are getting driven in one direction. So how in the world are we going to start to diagonalize the system? Well, it has, though it's not self-adjoint, it has a property which is called PT invariance. And this might be an abuse of the term, but it is used in interacting particle systems to be what I say here. What PT invariance means is that essentially the transition matrix or the Hamiltonian is related to its adjoint in a very simple way. So this system has a nice product invariant measure. So it has a nice stationary measure in product form, which can be written in terms of its kind of one-point invariant, or one-point distribution of having k particles at a given location, let's say the origin, in terms of ratios of these Plancherel symbols. This is, in fact, a generalization of what happens for all totally asymmetric zero-range processes. And there is actually a characterization of all discrete time versions which have the same property. Now, if you look in L2 of this, with respect to this invariant measure, and you look at the adjoint of this transition matrix, then it actually is up to conjugation by the parity transform operator that just flips you around the origin. It's essentially self-adjoint. Okay? So what it means functionally is just that if you can take right eigenvalues, if you can compute right eigenfunctions, then you get left eigenfunctions just by basically applying this parity transform and multiplying by this factor. So it's not an issue that it's not self-adjoint. You just need to deal with left and right eigenfunctions. And when you decompose initial data, you decompose it onto the right eigenfunctions, and when you recompose, you do it with respect to the left eigenfunctions. Okay. Now, in order to write down these eigenfunctions, I'm going to explain this classic idea of beta. And this is just a crash course, a primer on what is beta ansatz, what is coordinate beta ansatz, and then I'll apply it in the next slide. And you can keep in mind the example from before. I explained how the Q-Boson Hamiltonian takes a similar form. Okay, so imagine that you had that you're looking at eigenfunctions of a direct sum of one-dimensional operators. So you just have operators that act in a single coordinate of some space, and you just take the sum acting in each coordinate 1 through k. So before we just had these discrete derivatives in the coordinate 1 through coordinate k. So I'll call this curvy L. And then imagine that these well, you're looking for eigenfunctions of this. Imagine that you also want these functions to satisfy boundary conditions. Boundary conditions should act on pairs of nearest labeled coordinates, so I and I plus 1 coordinate, and it should be such that when you apply a boundary condition operator to your function and you evaluate it on the boundary, you get 0.
Is this the interaction?
This is the interaction. So in fact, in the case of the Q-Boson continuous time, it was just the discrete derivative in the first coordinate minus Q discrete derivative in the second coordinate. That was the boundary condition. Now, how do you produce eigenfunctions of this that satisfy this? Well, it's quite easy to produce eigenfunctions of this. You just need to find one-dimensional eigenfunctions of the kind of 1D operators, perhaps indexed by some space, for instance, C. So this, for each Z, you say have an eigenfunction. And now you take well, you observe that you can take arbitrary products of these. You can, of course, index them by different Zs. You can also permute the Zs, and you can actually multiply this by constants that depend on Z, only Z, not on the X's. So, well, the most general form is written here. And now you say, okay, well, what properties of these a sigma of Z's, of these constants or these functions only of Z, would correspond to satisfying the boundary condition? And luckily, well, you have boundary conditions for every transposition. And transpositions, they produce all permutations. So you can, in fact, find a sigmas that such that this satisfies this boundary conditions. And they're written in terms of taking products of these what are called S matrix terms, which can be easily constructed from the boundary conditions. Okay, so there's a very simple algorithm to producing these eigenfunctions. The problem is, as before for the usual one-dimensional Laplacian, is that we don't know necessarily which eigenfunctions participate in decomposing initial data, and we also don't know how to recompose these eigenfunctions. Okay? So this is what we'll really need to come into. There is one comment I make, which is I'm always dealing in infinite volume here. if you dealt with this system on some sort of periodic lattice, then you would have what's called quantization of the spectrum. There would be an additional set of equations called Bethe equations for these z's, and that complicates the whole story. By working in the infinite volume, we've much simplified our story. Okay, so how is the Q-Hahn boson process, how is it integrable? How does it fit into this framework of Bethe? Well, it fits quite nicely. You do the same sort of thing. You study what happens when you have k particles that are very diffuse, that are spread out. So this matrix has a very simple form when k particles are spread out. Each particle just either does or does not jump to the left. Okay? So what I've written here is this is the kind of transition matrix for k non-interacting particles just behaving as if they were alone in the system. This is, again, some deformation of the discrete derivatives. And lo and behold, in fact, using that special lemma that I showed you through which the Q-Hahn polynomial, or the Q-Hahn distribution came up, that commutativity of A and B lemma, you can prove that the following two-body boundary condition, if you impose this and you look at the free evolution equation, then the restriction to the ordered sets of coordinates is actually solving the Q-Hahn boson equation. So very much in the same spirit as I explained for the Q-Boson system, you have a free evolution equation, you have these k minus 1, you have these boundary conditions. They're slightly more complicated here. They involve the q's and the mu's and the nu's. Well, actually, they don't involve the mu's. If you impose the boundary conditions on the free equation, then you get that, that the free generator, or the free transition matrix actually corresponds to the Q-Boson one when restricted to the ordered Weil chamber. So this is exactly in the setup of being able to apply Bethe ansatz. That's the point. So here are the eigenfunctions. These are just produced from the Bethe ansatz. So this term came from this S matrix. This is the kind of one-dimensional eigenfunction. And this is this permutation. And now you see that between the left and the right, there's a slight difference. There's a minus sign that had to do with this parity transform. And then there's this CQ factor that had to do with dividing by the invariant measure, the PT symmetry. Okay, so writing down the eigenfunctions is perhaps not so hard or so complicated. And these are the eigenvalue equations that, again, come out of the Bethe ansatz. Now, there is something to be noted here. There's one remark that I want to make on this slide. Yeah? Oh, just because I reordered the ends. In fact, the ends should both change sign and reorder, and I changed that, so that's why I got Q inverse. These eigenfunctions only involve the parameter nu. The eigenvalues involve nu and mu. So in fact, I have, as mu varies, I have a one-parameter family of commuting operators. All of these Q-Boson transition matrices commute as long as nu is the same. Nu and Q are the same. This is akin to what happens in something like a 6-vertex model, any lattice model. Transfer matrices commute as long as the spectral variable remains the same. And the spectral variable here is really played the role of nu. Okay. That actually will come in quite handy for us. Now, in order to diagonalize and then ultimately solve this system, I need to describe the Plancherel theory. I need to say, how do you project onto eigenfunctions and how do you recompose with respect to them? So this is akin to what you do in Fourier analysis. So let me first define spaces. So the kind of space of functions that I'll look at is, for convenience, I'll look at functions of these sort of real variables, of these particle location variables, which are compact. So they're from this Weil chamber to C, and they're of compact support. And then the kind of dual space, or the momentum, the spectral space, will just be some space of symmetric Laurent polynomials in these Z variables. You shouldn't worry so much about the nature of these spaces. Now, I'll define a direct transform, an analog to a Fourier transform. And what it will do is it will take a function on the spatial variables, and it will just sum it over the entire Weil chamber, over all ordered ends, against the right eigenfunction. So you can think of this as some sort of bilinear pairing of the function f with respect to the right eigenfunctions under some suitable pairing, which is just described by this. Now I'll have an inverse transform. Okay, for the case of the usual Fourier analysis, inverse transforms and forward transforms look very similar. Once you go up to more complicated systems, you need more complicated Plancherel measures and more complicated spaces. Here, the space we're dealing with, these z's live in the complex plane. So I need to restrict myself to certain classes of these z's. And what happens if I want to apply this inverse transform from these space to this space, what I do is I take my function g, this is a function of spectral variable, I multiply by the eigenfunction, and now what happens is I'm going to integrate out the spectral variable. Here I summed out the real variable, got a function of the spectral variable. Here I integrate out the spectral variable, I get a function of the n's. But I do that with respect to a measure. This is the Plancherel measure. And you need to do this on the right space. And in fact, you have a little bit of freedom, but the freedom is only that you can integrate along contours, which are circles around the origin, including 0 and 1, but not including nu inverse. Okay, so this has, well, it comes out of the proof. This I'll call another inner product. It's between G and L, so I just write it in this form. It's basically integration against this. Okay. I'm going to explain how these two things are related, in fact, how they're direct and inverse transform. Let me just give a very quick and don't be afraid slide telling you that this formula, which is the one I just explained, this involved these large contours, including 0 and 1 and not nu, with this Plancherel term. You can manipulate it. You can massage it into different forms, which might be more familiar. So for instance, you can massage it into a nested contour integral form, which actually looks very similar now to the ones I showed you earlier in the talk. It had the ZA minus ZB and the Q, ZA minus QZB, this skew van der Waals term. You can also massage it into a form which would look familiar from Pierre's talk, which involves string states, which came from the expansion into the residues from this term here. And so in fact, for different degenerations, for instance, the degeneration that goes to the attractive delta Bose gas, you need to find the right saddle points. And in fact, you can only find those saddle points when you're dealing with the contours corresponding to these string states. And that's why you get string states. But once you've gone up high enough, it's kind of all interchangeable. Yep. Where the psi has been absorbed into this expression. So this came actually, both formulas, well, this formula comes from a symmetrization. In fact, this one as well. This is an asymmetric formula of the ends. This is a symmetric formula of the ends. So you've done a symmetrization. Okay, so there's some subtleties, but okay. So here's the big theorem. Fine, I got to it. The theorem is that these two transforms, this one and the J that goes backwards, are mutual inverses. So Fj and Jf are both the identity on their respective spaces. Of course, you can expand a little bit beyond their respective spaces. Additionally, they form an isometry. So this should look familiar from Fourier analysis. And these eigenfunctions, actually this is an implication, the eigenfunctions are biorthogonal many variable symmetric polynomials. In fact, very nice generalizations of Hall-Littlewood polynomials. If you take this inner product with respect to the spectral variable, you get the delta function in the real variable. If you take it with respect to the real variable, you get a delta function in the correct interpretation in the spectral variables times the Plancherel measure. The proofs of these results, in fact, let's say the proofs of these biorthogonalities are nice. The forward one, that JF is the identity, is actually a calculation of residue calculus. I'll have something to say a little bit later in relating this to the ASEP work of Tracy and Whittam. The dual result, in a sense, the biorthogonality, the second of these biorthogonalities, ultimately is due to the fact that there exists this one-parameter family of simultaneously diagonalized matrices. The fact that you could vary this mu parameter and have the same eigenvalues. So you can use that to impose certain relations, which ultimately give you this second biorthogonality. Okay, so how does one use this result? Okay, so it has a nice, pretty form. Is it useful? Okay, so here I can finally get back to the beginning of the story, which was I want to go beyond step initial data, and I want to see how far I can go and what are the challenges that you encounter. So as we said before, if we wanted to study the Q-Hahn TASEP or the TASEP type processes, duality told us that we could study the Q-Boson evolution equation with suitable initial data and that would suffice to compute moments. This was the analog of studying the delta Bose gas to compute moments of the stochastic heat equation. The challenge was it wasn't clear how to compute for arbitrary initial data, which one might be interested in. So, well, let's see what we get. So if we want to solve this for general initial data, you should take the initial data, you should turn it into, you should project onto the eigenspace. That essentially diagonalizes the action of the Hamiltonian, or of the matrix. You just get these multiplicative terms with the eigenvalues, and then you should transform back into the real variables. So it's a very compact formula, but how useful is it? Okay. Well, okay, here's another way of writing it in terms of contour integrals. And you see, in fact, this is exactly like the terms, the multiplicative term, this is this van der Waals type term, and this is the term which for step initial data always gave us the 1 over z expression. So how useful is it? Well, the problem is that this inner product, or this action of the direct transform, is itself an infinite summation. It's a summation over this Weyl chamber for the ordered n's. Now, I'm not claiming by any means that it's an easy calculation what that is for generic initial data. In particular, for flat or half-flat initial data, this is a hard calculation, and this goes in the direction of the work that Jeremy has been doing. There is a class of initial data which doesn't, to my knowledge, include half-flat, for which it's an easy calculation. And that is any initial data f naught, which can be written as j applied to some function g. Well, if you can find a g such that f naught is jg, then when you apply this curly f to f naught, you get fjg, which is g. So this is actually laughable, I agree. But take the function g to be this, and then you apply, j is just a contour integral, so it's quite easy to compute contour integrals by residues. And then you actually get a very non-trivial combinatorial identity, an infinite summation formula, combinatorial identity, which in particular for this initial data produces the 1 over z, and you can check that if you apply j to this function g, you get the initial data for step initial data. Okay. So in fact, there's a story related to McDonald processes and for what g's are meaningful, which I could go into if I'm not going to. Okay, so this is useful insofar as if you can compute this, or if you can guess a formula for this, then you can certainly check it in this manner. Okay? How else is this useful? Well, I promised that I would talk about relating ASEP and Q-TASEP. The relation to Q-TASEP is quite straightforward, or to Q-Boson, it's just a special parameter, set nu equals 0. How is ASEP, or the XXZ model, related to this Q-Hahn boson stuff? Well, it's not a degeneration. Let me repeat that. It's not a degeneration of the Q-Hahn boson process. However, its eigenfunctions are degenerations of the eigenfunctions, and hence it can be diagonalized by the same spectral theory. Spectral theory is something kind of disjoint of the Hamiltonian. There can be many operators that are diagonalized by the same eigenfunctions. The way that this degeneration works is the following. I set that parameter nu to be Q inverse. Okay, now, of course, this is outside of my initial consideration. I initially considered nu less than 1. Q inverse should be bigger than 1. So there's some work that needs to be done, a little bit of work in making sense of this degeneration, but it can be done. The reason why this Q inverse is nice is because it actually terminates most of these Q Plancherel symbols. So there are some nice simplifications. Now, if you take this degeneration, you can check that the eigenfunctions degenerate to those of ASEP. And in particular, this forward Plancherel identity, JF is the identity. What this tells me is basically how to take a spatial delta function and re-express it in terms of eigenfunctions. Okay? Well, that becomes equivalent to Tracy and Whittam's k-particle ASEP transition probability formula. So Tracy and Whittam had proved if you want to know the transition probabilities from ASEP in position y to position x, you write down this formula. Now, checking this really, you set t equals 0, and you get some complicated formula which needs to be the identity. It needs to be the indicator function x equals y. Now, you can do a little bit of rejiggering of this formula and express it in terms of eigenfunctions and in terms exactly of this expression. So you see that what Tracy and Whittam did was actually prove the forward Plancherel identity, just not in the form that I've written it. Now, there's one remark here. If you look in Tracy and Whittam's work, so proving the identity. So if you have the identity permutation, then in fact everything simplifies and you really do get an indicator function. So then you need to show that nothing but the identity permutation contributes to the initial data. And in their work, you actually needed to pair off pairs of permutations. It wasn't true that each permutation separately gave a contribution of 0 in this formula. There was a complicated pairing. In fact, when you go up to the level of the Q-Hahn boson process, in proving this type of result, you do get that each permutation disappears, aside from the indicator, or the identity permutation. And the reason why that breaks down, it has to do with the way that you take the limit to ASEP. So this is a simplification that occurs by going higher. The other remark I want to make is that if you look at the sort of the dual Plancherel, the fact that fj, so if you go from spectral variable to spectral variable, so that also degenerates to a result for ASEP, a general Plancherel result for ASEP. Now there is a special function g, not very different from the one I showed here, I just didn't write it down, such that if you apply fj to g, of course you get back g. On the other hand, this jg is just a contour integral. You can evaluate that explicitly, and you end up with an infinite summation formula giving you a very concrete expression. Now, if you look at equation 1.6 in Tracy Whittam's first paper, there's what's called a magical identity, and that's this formula. So in fact, their magical identity is a consequence of the degeneration of this dual Plancherel applied to a special function g. And then, of course, you can imagine now a machinery for producing other magical identities, which may have some interesting implication with respect to ASEP initial data. And that was actually a challenge going beyond step or step Bernoulli initial data in ASEP. And now this might present a means towards finding some reasonable class. The connection to XXZ and the XXZ Plancherel theory is that, well, in fact, there's a simple similarity transform, a diagonal conjugation, which brings the transition, the generator of ASEP into the the ferromagnetic XXZ Hamiltonian in the K-magnon sector. And then what that means is that these Plancherel theories actually become Plancherel theories for the eigenfunctions of XXZ, which are just easily recorded from those of ASEP. In fact, in some form, this was recorded in work of Babbitt and Gutkin. There was no proof contained there, and in fact, all proofs having to do with any of this seem to have been deleted from the history books. So we've searched for proofs of this, but nothing seems to have ever actually shown up. So one can reconfirm these types of results. Okay, so well, since I'm over time, let me not, these are degenerations, further degenerations involving the KPZ, the delta Boson gas, the various other things, Hall-Littlewood polynomials. Let me not go there. Let me just indicate some further directions and then close. So of course, asymptotic analysis is something I haven't gone into. Now we have these Q-Hahn systems. They certainly deserve their fair share of asymptotic analysis, convergence to the KPZ equation, various other degenerations. I didn't talk at all about algebraic beta ansatz. This kind of took over from coordinate beta ansatz. In the case when nu is equal to 0, this Q-Boson process, this came out, Sasamoto and Wadadi's work actually came out of this machinery. And so one should be able to develop the idea of kind of commuting transfer matrices and generalized XXZ, higher spin XXZ. It put this all into the general framework. These biorthogonal symmetric polynomials that are eigenfunctions are nice generalizations of Hall-Littlewood polynomials. They actually have nice properties in their own right as these biorthogonal polynomials. There should be, or perhaps might be, some relation to a higher lifting of McDonald processes. In the case of nu equals 0, then there is actually relation with difference operators, McDonald difference operators. This is a more probabilistic remark, which is that, in fact, there is a whole family of discrete time, totally asymmetric zero-range processes with product invariant measure. And I would hope somehow that the approach of Ballas, Kamyathi, and Sepalainen on continuous time zero-range processes, proving one-third exponents, might be extended to these discrete time results as well. So the summary is that I sought out to describe to you a sort of rigorous replica method, a way of lifting up and making sense of from a mathematical perspective, these calculations that physicists have been doing. In fact, we saw that by going up to these higher levels, we not only got a rigorous replica, but we got a lot of interesting mathematics. We were able to, in some form, create an umbrella for Q-TASEP, ASEP, XXZ, various other delta Boson gas type objects. We were able to prove Plancherel theories for these, which have some implications with respect to general initial data. There remains a very big challenge of turning all these algebraic advances into new analytic results, new asymptotic results, KPZ with various initial data. How do you get them out of this? This is a real hard challenge. And as I indicated on the last slide, there are many, many questions and directions. And I'll stop there. Thank you very much.